All right, let me try another hopefully helpful video solution here. It's from chapter 7, more on energy, number 25 here. And it starts off by saying, how high a hill can a car coast up? That is, if the engine is disengaged, if work by friction is negligible and its initial speed is 110 kilometers per hour. All right, so I've been emphasizing and want to continue that I start this conservation of energy, each of these conservational principles, whether it be momentum or energy, and say, okay, set them equal to each other. So at some beginning point equals some ending point. And keep in mind, it is just 2 points. It's not necessarily the final part of the process. It's not even necessarily the beginning part of the process, but really between 2 points. So I'll kind of think of maybe the car at the bottom of the hill and it coasts up to the top of the hill. And so there is the beginning, initial, down at the bottom of the hill, and here is the top, the final. And so 2 separate points. And it sounds like when we think about all the energies, and so I'll just write them out. I have initial kinetic energy, and I have initial potential energy, and I have work done by the non-conservative force. That has to equal the final kinetic energy and the final potential energy. Okay, now, in this particular problem, our object is moving, and so let me give it some velocity. But before I do that, let me just point out that they gave me 110 kilometers per hour. And this is a good chance to mention the units again about energy. Energy is measured in joules. Joule is a newton times a meter, and a newton is that kilogram meter per second squared. So I really need my distances in meters and my time in seconds. So I'll begin this with a little unit conversion and say, okay, I want to get rid of kilograms and have meters. And then, of course, to make it work, we got to make sure the number on the top equals the number on the bottom, so that way kilograms canceled and we've converted into meters. And the other thing we want to do is get rid of hours and make it into seconds. So I'll put hours in the top and seconds in the bottom. And again, for this to be done correctly, you can only multiply by a 1, so we need our numbers to match. And we know that there are 3,600 seconds in 1 hour. And so now hours are going to cancel. And so now we're going to get our speed in meters per second. And that's what we need to work with. So this, of course, like all problems, we can never forget chapter 1 and our unit conversion to make sure things match. So I'll take the 110 kilometers per hour. I'll multiply it by 1,000 and then divide that by 3,600. And so this is about 30.6. So 30.6 meters per second is the initial velocity. Okay, so you'll notice that they said, how high does it go? And they didn't even give me a mass. So I'm a little nervous about that, but I know that the other terms have mass in them, and hopefully they will cancel off. And I think that will be the case. So let's just keep going. So I'm going to put in my first step, the kinetic energy. The potential energy comes in 2 flavors, if you will. There's the gravitational potential energy, which is our mgy or mgh. And then there is the elastic energy of a spring, which is this 1/2 kx squared. And in this case, there's no springs involved, so I don't know if we should even waste our time talking about a spring, so I'll just cross that off and then not even worry about it on the other side. But there is a change in height. And so I will go ahead and call down this lowest point here 0 height, and don't need to put a number here. Of course, it will show up on the other side because that's the question, how high does it go? But I just wanted to emphasize that I am considering the gravitational potential energy. Now, the non-conservative force, I'll put a 0 also, because that would be the friction or something else pushing on it, like the engine engaged or something. And we don't have that, at least for A. I think it's going to change here in B, so I'll put a 0 there. And if, of course, the question is how high of a hill could it go, we're going to say, well, it gets 0 kinetic energy at the top. In other words, it just barely makes it to the top of that hill. Or if it's a ramp, it goes up and comes to a stop. And, of course, then it goes back down unless we put our foot on the brake. But that is a final speed of 0. And then we would have an M, a G, and a final height. So all of these pieces have a lot of zeros in them, and it's really just saying the initial kinetic energy here is converted fully into gravitational potential energy on the other side. And each of them have an M in them, and so we can cancel that off. And so now we can grab the calculator, and on this side say 1/2 times, I'll just go last answer, squared, and that'll be the left-hand side over here. Then if I divide by 9.8, I get 47.6 meters. So it'd go up a pretty good size hill coasting at this speed if there was no friction. However, let's take a look at B, which says, if in actuality a 750 kilogram car with an initial speed of 110 kilometers an hour is observed to coast up a hill of only 22 meters. So really less than half above its starting point. How much thermal energy, so heat, that is this number right here, the work done by friction. How much thermal energy is generated by this friction? All right, so kind of along those same lines of thinking, let me write out the initial kinetic energy. And this time they give me a mass to work with. And so there's the initial kinetic energy. I'm going to say the same thing, that it has no gravitational potential energy. Of course, what's different from A is we're going to put a number here, so we want to know what that number is. Because over here on the right-hand side of the equation, we say just barely gets to that point up the hill, or comes to a stop at the height of our 22 meters. So this would be M, G, and our height would be our 22 meters. And so now I can figure out how much work is done by this non-conservative force. Okay, so I'm going to take the 750 for the mass, the 9.8, and the 22, and subtract the 1/2 times 750 times 30.6 squared. And so, not a surprise, it's a negative number. And I'll just call it 189,000 for significant figures. And it is an energy, so I'll put it in joules. So there is our thermal energy. Although maybe really what they want us to answer is the positive 189,000 joules. Because usually we say that the heat is the negative of the work. So they really ask for the thermal energy. So I'm going to give a final answer as a positive. But I think they could be more clear on which one they wanted, but I really think they want the positive one here. So this is the work, and then this is the energy. Okay, then the last part of this is kind of a piece of this chapter, but a piece of previous chapters where it says, what is the average frictional force if the hill has a slope of 2.5 degrees? So the hill is sloping up like this. And what we worked out in our derivations is the work done by friction. So the non-conservative force had this minus the force of friction times distance traveled. And we got that from that cosine of 180 degrees as we did our calculation for work. And so there was our little integral that I said, hey, I'll set you up for this chapter and I'll do these integrals. That's how we got the 1/2 mv squared. That's why we didn't need to do it. And then we don't need to do this integral. That's how we got it. And of course, we also did the integral to get the mgy too. So we set ourselves up to prove how and why conservation of energy works. We did those integrals. It's an important thought process. It kind of gives us some confidence in why it works and how it works and what the symbols mean. And the best part about it, then it just gives us one big equation of conservation of energy that now becomes an algebraic problem for us to solve. And that's really the technique I'm trying to illustrate here. Is there's no components. You notice that these are scalars. There's no sines or cosines. Anyway, so this one was, again, like the others, 1/2 mv squared and mgh or mgy. This is already done. Of course, now we need to go back a couple of chapters and say, look, back in chapter 4, we said the force of friction was the coefficient of friction times the normal. Oh, and I apologize. I guess we don't have to go back that far because I'm just reading it. See, again, it says, what is this average force of friction? So I first read it as what's the coefficient of friction, but we don't have to go back that far. All right, so we just have to do this. And so we know this number. This is the negative 189,000 joules. Then we have the negative force of friction. And we're going to have to do a little either geometry or trigonometry here to figure out the distance it traveled, because it goes up the hypotenuse, but we know that the vertical height is 22. That was the given part of the problem, and we know this is the 2.5 degrees. So it looks like we got the angle, we got opposite of it, and we want hypotenuse. That sounds like a sine function. So sine is 2.5 times 22 over distance traveled. And so distance traveled would be 22 divided by 2.5 degrees. So 22 divided by sine of 2.5. And so this is 504 meters. Okay, so I'm going to put this over here, 504 meters. And I'll also remember then, in this last step, that a joule is a Newton times a meter. So the meter is going to cancel off, and I will be left with units of newtons, as I should be, since I'm looking for a force. Okay, so I'll cancel off the two negatives and then type in 189,123,000 divided by a distance of 504 meters and comes out to a friction of 375 newtons. All right, hope that's helpful.